So let me recall where we were, which is to say that there was this Navier-Stokes equation, which we started with. So this is what the starting point was, a fluid with some external forcing represented by this, viscous dissipation, and the pressure gradient, the internal pressure gradient over here. This, the acceleration, V alpha dot, the total time derivative, V beta, del beta V alpha. And this is all for divergence-free flow. That's an incompressible fluid with this constraint over here. And the interest is in solutions which are essentially nonlinearity dominated and seemingly random. So that it's instead of talking about V alpha, R, and T, more sensible to talk about probability distribution of something or other. And so what we did was, as a first exercise, looked at the energy balance of this system over here, and the kinetic energy, total kinetic energy was taken as E equal to half, and then V square D3R. We talked about, we did averaging over the volume, so that this was half V squared D3R. So this spatial average over here is effectively an ensemble average, and this is your half V squared. And the result that we got for this was that dE dt is equal to minus nu del alpha V beta whole square, so viscous dissipation plus average F alpha V alpha. So this is the rate at which we were injecting energy into the system. This is at typically large scales L. And this is where things were getting dissipated, and the viscosity in general is pretty small, so this would have to be big. These derivatives are big at small scales, so this is operational at small scales on LD. And the point is that if you want stationary turbulence, so turbulence has to do with the question of seemingly random solution of this Navier-Stokes equation. You saw some pictures, courtesy Rama, in the last hour. So stationary, meaning that there is a balance. If I did not have the balance, so for example, if I was not putting energy into the system, then dE dt is negative definite, and the energy would go down with time, and all motion would stop. On the other hand, if I did not have this dissipation over here and kept pumping energy into the system, E would blow up, and you wouldn't have a manageable situation either. So you have this thing, and a stationary situation is possible, provided nu del alpha V beta whole square is equal to epsilon. And this was the crucial business, because epsilon is independent of what nu is, so I can happily take the limit of nu going to 0 and still have this relation fulfilled, and therefore you can see that this expectation value has to go to infinity so that the product is finite, and this is what is the ruling principle, the so-called viscous anomaly. So nu goes to 0, gradient blows up, keeping the average of this gradient squared times the viscosity a constant. And if when we worked out these scales, L over LD, they turned out proportional to Reynolds number to the power 3/4. And so this corresponds to Reynolds number going to infinity. This nonlinearity dominated. That meant that Reynolds number was much greater than 1. And so in this limit of Reynolds number going to, and we have this picture where essentially this is a dissipative length. Here is the small scale L, and this is the energy input length over here. And you have this transfer energy in at epsilon, energy dissipated over there, and a transfer across the scales, which is this inertial zone. And in this limit of Reynolds number going to infinity, the LD is sort of squished to 0. You have only one length scale in the problem. In the inertial range, when you talk about, I mean, this is where Kolmogorov comes in to the picture, K1941, generally referred to as that. What is it that one wants to talk about now that we know that the problem chap is this derivative over here, which is essentially V at R x plus R minus V at x. That's the chap which is the problem quantity. So the probability that you want to talk about is that probability distribution is that of delta V. And that's a far more difficult question than talking about the moments. The moments were obtained through a dimensional analysis by Kolmogorov, which told you that this was epsilon to the power n by 3 r to the power n by 3. And if in this limit of epsilon, the Reynolds number going to infinity, there is just one scale in the problem, which is this capital L, there would be some function r over L. And so long as there is limit r over L going to 0, f the limit of f as r over L goes to 0 exists, you have don't have a problem. You have delta V to the power n given by this, coming out of purely dimensional analysis. Coming from the picture that here sitting in this inertial range, I don't know about this, I don't know about that. The viscosity of the fluid cannot have a role. How I'm injecting energy can't have a role. So it's only epsilon, which is the energy being transmitted. It's only the scale at which I'm observing things. And this would be it. If I'm unlucky enough to have the F blow up on me as R over L goes to 0, which during the afternoon session yesterday we saw meant that essentially this energy dissipation, this energy epsilon, the transmitted energy across the scale, is not really a constant but has fluctuations, intermittent fluctuations. That's when F R over L tends to blow up as R goes to 0, has some characteristic behavior. If it is n, some n over here, there's some zeta n over here. And that is the phenomenon of intermittency, this chap blowing up. Your the answer is no longer n over 3, and the sort of shocking business is that within the Eulerian framework of hydrodynamics, it seems that I cannot have a way of generate analytic technique for calculating these numbers zeta n. So they exist, the real, whether experimentally or numerically, you can see that these numbers do exist and things are sort of problematic. But within Eulerian framework, I have no handle yet of getting these numbers in an unambiguous manner. There are various ways in which you can approach the problem somewhat tangentially from various sides, but it's a bad thing not to be able to get a better handle on it then. So this is all that we did yesterday. So I mean, we want to pick up from here, and we want to pick up from here with now doing, at least sketching for you, the anomaly once again in very clear-cut terms, because Kolmogorov did do the calculation exactly starting from Navier-Stokes equation for the case of n equal to 3. So n equal to 3 is vital. N equal to 3 was vital to this whole business because that's where the calculation could be done. And what exactly are we going to calculate? Now I'm going to have to explain to you why, I mean, I write vectors all over very carefully when I'm doing this. I have not written the vector velocity over there. What exactly does delta v to the power n mean? And so I need to clarify that. What it means is that it is v vector Vx plus r minus Vx. In writing this, almost, I mean, it seems that I have forgotten that V is a vector. And so then you do this, and to make things a scalar, you take a dot product with this separation vector r. So it's a projection of this velocity difference on the vector r. And then so it is this chap over here raised to the power n. And this is what technically this business is. So delta, when one writes casually delta v to the power n, what one is, I mean, after all, you are dealing with a velocity vector. What you mean by that scalar over there, that this, it is this chap over here. This is the definition of delta v of r. All right, so what Kolmogorov proved was delta v cubed, this is equal to minus 4 by 5 epsilon r. So now what are the ingredients of the proof? I will not prove it, but I'll make it pretty clear that this is what. So the vital thing, I mean, it is all the ingredients that we had yesterday. They are the ones which have to come up repeatedly. So the first thing I had was stationary. So stationary has to come up. Stationary has to come up. And so what does stationary mean? Stationary means that this, if I look at correlation, U alpha x on U beta y, that at time t, for example, this would be in the derivative del t of this would be equal to 0. So that's what stationarity means. So stationarity would give you this picture that it's a time derivative. This correlation function over here is independent of time, which would mean that u alpha x t plus dt, u beta y t plus d, that's equal to u alpha x t u beta y t, that. So that's stationarity. So stationarity means that it's the same at all times. So at time t, this correlation function calculated at time t is the same as this correlation function calculated at time t plus delta dt. So stationarity is the first ingredient we had, and stationarity is what will be the first thing which we want to talk about and exploit. So, all right, now what is the dynamics of U alpha? Dynamics of U alpha, I've been told, is del U del alpha dt is minus del alpha p plus u beta del beta u alpha plus the external force F alpha. Now this external force over here, it's convenient to take this as after all, what we are saying is that what the velocity field that we are talking about is a random variable. So its F alpha can be taken as a random forcing, and with a correlation specified, which is F alpha x T1 F beta y T2 is equal to some function c of x minus y delta function of T1 minus T2. So this Markovian correlation of the random forcing x1 f specified through its correlation function. Good. So that's clear. Now, all right, so what do I have to write? I have to write u alpha x of t plus delta t. So what do? I just integrate that out. So u alpha x t plus dt is equal to, simply integrate that out, integral from t to t plus dt minus del alpha ps plus u beta s del beta on u alpha s plus f alpha s ds. Right? So this is it. So this is the u alpha x t plus dt plus this. So now imagine writing it out. This is going to be plus, yeah. So that plus this integrated between t and t plus dt. Yeah. Negative sign on this. Right. Good. All right. So smooth chap here, no difficulty. So this term would be integrated out. This would give you something times dt. That is minus del alpha p t times delta t. So this integral would be just, the mean value theorem, and this is times delta t. Similarly, the mean value theorem over here, and times delta t. Now, this one over here, this is not the f alpha s ds. Here is f alpha correlation function over here. So F alpha times ds, when integrated out, the delta function over here is like 1 over delta t. Therefore, the F alpha is like a 1 over square root of delta t. So this chap over here, mind you, is integral. So it is F alpha s delta t, but this is not really of order delta t. So F alpha, if I write this as F alpha t delta t, you are actually looking at this F alpha, which is of order 1 over square root of t delta t, and therefore you have to beware that while these are chaps which are order delta t, this is not of order delta t, it is square root of delta t plus u alpha xt. Good. So now, I mean, with that clear, you can see now that if I look at this product, I have written this out, I have written this out. Yeah, go ahead. One over square root of delta t. Yeah. Square root of delta t. Yeah. Now, yeah. Huh? Which one do I want to drop?
The linear.
No. Where is my del square? Gone for a walk. Yeah, right. Sorry. I mean, the vital stuff gone out of the thing, right? Sorry about that. New del square u alpha, the same stuff as going from t to t plus delta t. And so another delta t chap over here, del square. Yeah, sorry. All right, very good. So here we are. And now imagine that I'm multiplying this by this and working to order delta t. So I'm going to multiply this by this, and I'm not going to write it, but just, so here we are. There will be a u beta from here, there would be a u beta term coming and multiplying this one over here. That would be your term which is of the of order unity. So that would cancel this. So that's gone, right? As expected. Then there are these easy ones which are of order delta t. So those are of order delta t, and they would get multiplied by just u beta y of t. That is when I 0 equals 0, because from that side I have cancelled this chap over here. So it is 0 equals what? Now 0 equals this minus del alpha p x t u beta y t, and then it is minus u beta t, sorry, keep the x t del beta u alpha x t u beta y t. Should have this is should have actually gone for a gamma over here if I'm going to keep that. Sorry. Right. Yeah. So the dummy index I should have, been careful enough to. Minor, but honest. So plus new u beta y t del square u alpha x t. All that very clearly dt order dt terms. Now comes this one here. This chap, when it gets multiplied by the u, so the similar expansion, the order, zeroth order term from here, u beta, that multiplies this, and you would feel that, aha, you are sunk because this is square root of delta t, but then the averaging comes to your aid, and average average over the ensemble, f alpha average, gives you 0. So you don't have to worry. The pesky square root of delta t term is 0 after you have done the averaging over the ensemble. So that is gone, and you don't have to worry. So which is the one which you have to worry about? You have to worry about the one which is 2 f alphas. That's the one which you need to worry about. So I have to worry about f alpha, f beta, dt ds integral, and this chap, so this is 0, I've got all of them now, and this over here, so all these are, this over here, all these are of order delta t, and now this chap is of order delta t because one integration over the is an integration over delta function, and you have c x minus y, and then that integration gives you this, and the other integration is going to give you delta t. So this is of order delta t. All these chaps over here are of delta t, and there is a term where x goes to y. So add them all together, and where do I stand? Where I stand is that so everything is of order delta t, and what you are looking at is minus del alpha p u x t u beta y t, that minus u gamma x t, so expectation del gamma alpha x t u beta y t plus nu u beta del square u alpha x t, that plus c of x minus y, plus the whole thing with x going to x and y interchanged, that's equal to 0. So that's what up to order delta t, that's, we have kept all the terms, and they have to be equal to 0 because of the stationarity condition. So a lot of algebra, but at the end of the day, I mean, whether you have done the algebra or not, at least, I mean, this is what it comes to. I mean, there is a pressure term multiplied by velocity. There are 3 velocity terms over here leading you, which is what I want to get at. So I've got my desired 3 velocity terms. So there is this term with 3 velocities over here. There is a viscous term. There is an external forcing term. Huh? I got them all. Good. Having got them all, what am I going to do? So what I'm going to do is, first, the usual tricks that one is always up to over here. Number one, I mean, I'm going to look at things with written down in all generality, take beta equal to alpha. So beta equal to alpha to make now, so this would be true in general for any arbitrary alpha and beta, and that can be a starting ground for proving certain other things. But right now, I mean, I can make life simple for myself, keep beta equal to alpha. And so here we are. So beta equal to, if beta is equal to alpha, so I'm going to make that switch everywhere. So make this, so there was alpha beta over here, so that's become a trace. There is alpha beta over here, so that becomes that, and we are all through, set. So, all right, now look at what's the trick that I'm going to pull? This is a derivative with respect to x. This one is y. So here is the series of tricks that one does with these things. This derivative is with respect to x, but that chap is y. So I can as well bring out this x derivative. Mind you, this x is a sub, and it is p of xt and u alpha yt, right? So I can pull this out, because when you take it in, it will only be acting on this, the other chap is y. But now there is translational invariance, there is a function only of x minus y. So I can shift this, make this a y derivative with a change of sign, because the whole business is a function of x and y, is a function of x minus y due to translational invariance. And then before you can say anything else, I just take this inside again and put it over here. And I put it over there, but then del u alpha del del alpha of del u alpha is 0. It's an incompressible fluid. So there you are, one term out, right? So this is the trick. So this is gone. So that chap will not be gone, because if it were gone, you would be not in good shape. So you want, that's the chap which you would have to keep. This one over here with this alpha has become, but what is this? This over here, this there was this y over here, and there is this one. So you can do this shifting of your x and y once again at your will. And what is going to happen is that you can put a y over here and a x over there. This becomes the usual dissipation form, that it is a derivative of one grad, and the one is at u, and the others at y. So this dissipative chap over here, playing the same game, becomes that. And there is this trace over here. And there is this third order chap, which I would have to manipulate. Now, here again, I mean, you would have to play around with the indices and with this del. There are a set of identities over here. And at this is where I will just write down what you are supposed to get. And what you are supposed to get with that is, it's quite logical, so you should not be complaining too much about what one is going to get. That, all right. So 1 derivative and 3 u's, right? So that is what you should be looking for. So your final answer should have 1 derivative and 3 u's. And that's what it has at the end of the day. It is a question of writing this as minus 1/4 del j with respect to x variable, it is uj, all right, ujx minus ujy into uix minus uiy into uix minus. So that's the manipulation for this term over here. There is one derivative, which is this derivative over here, and there are three velocities, the three velocities, so it's a product of three velocities written out in this x minus y form. So a whole lot of identities which go into getting you this result. That's a lot of algebra, so that's the part which I'm skipping, plus trace of cx minus y, that should come with a half, right? Yeah, it does. So that's half, and that's on the other side. So this is equal to, and there is the dissipation, which does not have a half here, right? So plus nu del I u x del I u y. Right, so this is the story at the, after you have done everything, and that is, everything means just this 3-point function manipulating the 3.1. So that's the doing business. So the rest of it is, more or less was there in front of your eyes. It's this manipulation which was not, but here we are, and we are almost at the end of the story. Now you see, I can do two ways. What do I need? I need to get the dissipation. The dissipation, as you can see, is this quantity over here, which is evaluated at the same point x and y. So I want to take the limit of x going to y. That would make this the dissipation. And I want the Reynolds number infinity limit, so I also want the limit of nu going to 0. So I want x going towards y. I want, because after all, I'm interested in small values, very small values of r over here, which is the difference between x and y. So I want x tending to y. I want Reynolds number infinity, nu tending to 0. So I'll do, number one, x tending to y first, and then nu tending to 0. X tending to y, this goes to 0. X tending to y multiplied by nu tending to 0. So x tending to y, this is epsilon, and this is the viscous anomaly, that limit nu tending to 0, nu, this average square is equal to epsilon. That's what we know. And then I'll do it second way around, that it is nu tending to 0 and then x tending to y. So it is, this is nu tending to 0 before I do x tending to y. So this is gone now. And this is still this epsilon, x tending to y. Your half trace this is equal to epsilon. So now you have epsilon, and you have minus 1/4, and there is del jx with these, all these things, with x tending to y. So x and y very close to each other. And that's it. Therefore, you're you are through. You have this on one way of doing it leads you to this. The other way of doing it leads you to epsilon equal to minus 1/4 this over here. Now you can integrate out. So you can write this as the standard, one more step to write. You take your x and y, take y equal to 0, and your mod x much smaller than 1. So you have your ux very small x, ux minus u0, ux minus u0, ux minus u0. And you can imagine that you can see very clearly that if you integrate it out, it's epsilon on the other side. That correlation is going to be epsilon, which is this quantity over here, times a linear thing. It looks like x over here, but then you know that the quantity that you are after is x dot x, I mean, it's the x component of this times the times x, y component times y, z component times z, all the spherical symmetry and so on and so forth. If it is now in d dimensions, forget d dimensions, in d equal to 3, you get the desired result that delta v to the power 3 average is minus 45 epsilon times r for very small r. So this is what you get. It's very clear from here that you can, I mean, it's going to be linear in the coordinate, and this coefficient over here is doing the integration correctly, and the angular averages correctly. So doing the angular averages, doing the integration ensures that the power would be 1. The angular averages ensure that this coefficient will be 4 by 5. Epsilon is already there, so that is it. So this is how this anomaly, once again, it's this question of this anomaly over here, the dissipation rate. The dissipation rate is equal to this energy input rate, and you have this result over here with this epsilon sitting over here, which is both the dissipation rate and the... So the whole picture of this cascade and the scales and the fact that you have a small r result for this business over here with the f well defined to be exactly minus 4 by 5 as r goes to 0 is completely encompassed in this result over here. So that's why it is a tremendously important, I mean, the importance of this result cannot be sort of, it's not really, I mean, the importance is quite tremendous. It can, in various ways, it can be, it's a great help, and it is also a great obstacle for people trying to cut corners. I mean, here is an exact result, and imagine the difficulty it's going to put on your path. That if you are going to fool around, if you are going to do an honest calculation of this over here, then zeta 3 has to be 0. So zeta 3 has to be automatically 0, and that's what an honest calculation had. That is, if you could really do it. Otherwise, if you fool around by doing a little bit here and a little bit there and getting it, your zeta 3 would not be coming out to be 0. And you would have to put that in as a constraint and put the get the zeta 3 equal to 0 and get your answer out. So this is actually a great check on how well are you doing with this question of trying to get these exponents zeta n over here. If you are doing approximations, or if you are sort of model building in some way or other, this stands as a result which you cannot bypass in any way. So an exact result, an exact result which actually is in agreement with the simplistic scaling law that you have. And it shows the viscous anomaly, it shows everything that turbulence is all about. And therefore, this is, I mean, as Frisch's book describes it as Kolmogorov's 4/5 law, and that's what it is. There are other, you can get this is in d equal to 3, you can get a similar thing in d equal to 2, but all right, and similar other, various other correlations in d equal to 2, which are interesting, but this over here was the first of its kind and is very important. So this is it. So anything, I mean, probably worth my while to stop here. Any questions that you can, that you have on this? I mean, this would be apart from the mathematical manipulations which I have left out, which are trivial, whatever you feel like asking, this is probably a good time to ask. Yeah, because it's a small r, no? The difference between x and y has to be very small, so it is in a range where. I mean, do you get the hang of the calculation? It's a stationarity has gone into it, the anomaly has gone into it, and then playing games has gone into it. But at the end of the day, you have a solid result. Well, at any other time also, I mean, but this is it. I mean, whenever you want to whenever you have any doubts about it. So, yeah, go ahead. I mean, what I've written is this quantity over here. Yeah. So that square. Yeah. It's so, all right. But now everybody talks about, I mean, you must have heard, I mean, the GK tells you that Kolmogorov gave a 5/3 law, right? I mean, not a 4/5 law. So what has gone wrong? I mean, is 5/3, was that a popular belief which is really 5/3 or 4/5, or is there a 5/3 law? Well, the point is there is a 5/3 law, and that has to do with something called the energy spectrum. So I need to define an energy spectrum. Well, E is the total energy, which we have talked about so much, which is V square D3R, average V square, which is this. If I looked at this in Fourier space, then there is your Parseval's theorem, which would make this V. Okay, so this was your V square average, and with Parseval, this would become Vk in Fourier space, Vk minus k, this integral integrated over d3k by 2 pi cubed. So V squared d3r, that's your Vk V minus k d3k over 2 pi cubed. And this is your E, which, so that's one way of writing E in terms of the correlations. And this is d3k is 4 pi k squared dk. So you take the 4 pi k squared into this over here, and therefore you can, and with that you define Ek as this over here, with Ek being equal to Vk V of minus k divided, times 4 pi k square over 8 pi cubed, right? So this is Ek. Ek is, the spectral distribution of E, integral Ek, and it is, in terms of the correlates, it is Vk V minus k 4 pi k square. And had this been statmech with equipartition, then this would have been a constant and your Ek would have been k square, but it is not. The equipartition and statmech, Ek is to be obtained once again from dimensional analysis, Ek determined by epsilon and k. Do a dimensional analysis, E of k is equal to constant, call it C, and then it is epsilon to the power 2/3, k to the power minus 5/3. So that is the 5/3 law. Ek equal to C epsilon to the power 2/3, k to the power minus 5/3. And you actually can measure this experimentally with a pretty good degree of accuracy. Numerically, you can push it pretty hard. And the answer is really as close to 5 minus 5 by 3 as you would like to get. So, it is now that of course would, all this while I have been saying that there is this intermittency and these zeta n's, it's only n equal to 3 where it is 0, zeta n is 0. What happened to zeta n? Well, there is this rule of thumb that the zeta n's increase, zeta n's become observable for large n. So the deviation from Kolmogorov are actually high, as in the tutor for larger n equal to 6, which we talked about in the tutorial yesterday. That's where you see it very clearly. But for this 2-point correlation function, which determines the energy spectrum, it is k to the power minus 5/3 for whatever you are worth. So, all right, so that's 5/3 law. That's the 4/5 law. We have the inertial range, and we have. But now, so what else? What else is? Let's look at something different. Yes, need to now leave. I have had a lot of Kolmogorov, and energy. Let's look at something else, which is if I wrote del V del T, started with this equation of motion over here. You have, so let's forget the external forcing for now. Del V del T plus V dot grad V, that's my Navier-Stokes. Let me talk about the thing which you heard in the last hour, this vector called the vorticity. The curl of V. So vorticity vector, which we haven't, it's good that you saw in the lab that vorticity is an important thing. It has to do with the circulation of the fluid, because circulation, if there is a curve along which this fluid is circulating, the integral V dot dl would not be equal to 0 if you have a circulation around this curve over here. And then by Stokes' theorem, this is going to be equal to curl of V dot ds, where ds S is a surface whose boundary curve is this C over here. So a circulation fluid with a circulation, so having these circular circulations going in, would have a non-zero vorticity from Stokes' theorem. So pictures of turbulence are full of these circular closed loops doing all variety of things. So circulations should be important somewhere, and vorticity has to be important. So vorticity is the thing which one would like to look at. So what would be the equation of motion for vorticity? Well, equation of motion for vorticity would be, I just need to take a curl, but before taking a curl, let me write this as identity for a divergence-free fluid, V dot grad V. So if you took a gradient of V square over 2, that would be V dot grad V square over 2 minus, well, minus plus, one will know it when one is. So that's identity, give or take a sign, grad V square over 2. So, all right, let's see. Could be a plus over here, but one would be over, clear in a minute. So I want to, so this is equal to V dot del V, this is just a vector identity, minus V cross omega over here. So now you want to take a curl of this, right? So you want to take a curl of this to get d omega dt. So you get a d omega dt. You want to take a curl of this. Curl of this is going to be, this curl is going to be 0. So you are going to be left with curl of V cross omega. This curl is gone. This is equal to nu del square omega. So vorticity has this form over here. And if, so it is this, it has to be V dot, so curl of this is one grad on something and the other on something. The sign has to be such that it does need to be that, and if I've got the sign here wrong, the which is minus which, then you can blame it on the other identity. The final result has to be this. So final result has to be this over here. And now you can see that this term omega dot, so there is a, this is the build-up of the vorticity. This is the build-up of the vorticity, and this is the term over here which is going to help in the building up of the vorticity. So in this three-dimensional turbulence that we have, this vorticity is going to play a very big role. There is this vortex stretching that happens, and it is because of this term over here. So that's the reason why these 3Ds have the turbulent behavior in 3 dimensions, shows a lot of structure, shows various kinds of circulations moving in around there. So that's the, but suppose I were in d equal to 2. If I were in d equal to 2 and start talking about solutions of Navier-Stokes equation, and I wrote the equation for equation for this vorticity, well, this d equal to 2, I have a velocity vector which has 2 components, and it's a function only of x and y. Omega, so omega with the curl of v, in that case is only in the z direction. So omega is a vector in the z direction in d equal to 2. So omega dot del can only have a z derivative, but v is only a function of x and y. So in d equal to 2, this term is gone, and it is del omega del t plus v dot grad on omega is equal to nu del square omega. So what was this chap over here? What was velocity in this three-dimensional case being carried by over here, transported over here, and this is again, I mean, sort of icing on this transportation business with the new, here is omega being transported by this velocity over here with a new del square V. So if you looked at this energy balance, omega squared d2r divided by the area, this as your total something or other, let's call it S, then that would turn out to be a conserved quantity in the inviscid limit. That is, ds dt would be equal to minus nu del alpha. Clear or not clear? Yeah, five more minutes, yeah. I'll be through, really. So ds dt equal to minus nu del alpha omega beta squared. Are you clear with that? That I take a dot product, this dot product, integrate over all space, this is going to be 0 exactly in the way that integral turned out to be 0, and so it is this which is. So in the inviscid limit, the in the inviscid limit, your this integral, this quantity which is called entropy, omega square business. So kinetic, what was the kinetic energy is now called entropy. Is conserved quantity. And once again, there is the viscous anomaly that comes from over here, that this is if there was an external term which was generating vorticity, which would be this curl F over here. So if I had this curl F chap generating viscosity, entropy, then there would be entropy in term over here, entropy in term over here, and that would depend on the properties of F, which is acting at the boundaries. So large scale, small scale, viscous anomaly goes over here, entropy flows from high scale, from large length scales to small length scales. So just as you had energy flowing in d equal to 3 from large scales to small scales, here it would be your entropy flowing from large scales to small scales. So it would be, and the Kolmogorov argument now for the energy spectrum. So for the energy, there would be this energy spectrum, let's call it EK, that's what one is interested in primarily as something. So E of K, which is the energy spectrum, would now be determined by entropy flux, and this dissipation entropy flux and K over here. The dissipation rate is the flux which is getting dissipated. So whatever is this entropy flux, if I call it epsilon S, now you are supposed to do this. So this is an exercise. If this is epsilon to the S to the power M and K to the power N, M equal to what and N equal to what. So that's an exercise for you to do. That is this flow over here. Now, what about the energy? Energy is also a conserved quantity. So the total energy is also conserved. What about that? Why doesn't, what's going to happen to the, so I'm putting in energy over here. The entropy flows on this side. What happens to the energy? The energy actually flows backwards. So there is a theorem called Fyotov's theorem, which is sort of like an equipartition argument, and that essentially tells you that energy, there is energy flux also, but energy flux is backwards. So energy goes, E of k is still epsilon to the power 2/3, k to the power minus 5/3. That's determined, that is the energy spectrum determined by the energy flux. This is energy spectrum determined by the entropy flux. So if you are looking at these wave numbers, which are largish wave numbers, and looking at the energy spectrum, where it is the entropy flux which dominates, you would pick up something else which you are going to tell me tomorrow. And over here, it is this energy flux. So the last comment on this, that suppose I have yesterday one talked about these rotating fluids. So I have a rotating fluid, omega in the z direction. So, and I write down the equation of motion. That would mean that there would be, as you saw yesterday, a Coriolis force, additional Coriolis force over here, which is 2 omega cross v. The Coriolis force would be dominant for Rossby numbers. Rossby number is defined by average, some kind of average velocity v bar L divided by omega. So this is when the Coriolis effect is very big. That is, this term divided by this term is, that's the measure of this force, nonlinear term divided by this. Rossby, when Rossby is small, this number loses out and this dominates. So Rossby number tells you whether rotation is important or not, and that happens at low rotation speeds. So there is this point that one thinks that if I have a omega, the thing spinning around in this direction, then things would, because of the Coriolis force, sort of become two-dimensionalized. So that is from d equal to 3, you have started with a system. Here is, this says your system in a large box, and this box is rotating in about the z-axis. And there is a sort of belief that, look, things become two-dimensional, and two-dimensional is two-dimensional is like being sort of confined to the plane which is perpendicular to the z-axis. So it would be sort of things happening in the xy direction. Well, what does it mean so far as this is concerned? Suppose I go to large, very low Rossby numbers and look at this, what's going to happen? What's meant by two-dimensionalization? Two-dimensionalization would mean that it has to be that the spectrum has got to change. There has to be the effect of two-dimensionalization. That's the two-dimensionalization, and it is not, it cannot be, this is a very different, there is two-dimensionalization in this case, but not two-dimensionalization in the sense that things are all happening in a plane. Doesn't happen. You have a z component of the velocity, and although you may be sitting on this plane over here, things, let's say, have sort of squished you to a plane, but squished you to a plane does not mean that your velocity, there is no vertical velocity at different xy points over here. So W, as a function of x and y, there is no reason to believe that the third component of velocity. So saying that, the point is that from two-dimensionalization means that there is this Kolmogorov spectrum minus 5/3 is going to go over to a entropy-dominated spectrum. That is, you would have entropy conservation law is not there. That's not the picture at all. So there is no doubt that there is two-dimensionalization. If you the spelling is a bit problematic. It's waffle, or, I mean, this could be sort of interchanged, Smith. These were the people who in the late 90s got the picture that there is the clear-cut two-dimensionalization. The spectrum changes and is no longer minus 5/3, but neither is it this n which you are going to find. And also the point is, what is the flux? There is now the flux over there. It is still a three-dimensional thing, and the relevant flux is that of something which is called the helicity and defined as omega dot v. So omega dot v, which is a helicity, is something else which we have not talked about. So this is an opening. Now, what are you going to do? You have to find out that what del th is equal to. So that as a homework problem. So this is going to be some minus divergence of some helicity current plus a dissipation term over here. So you are supposed to take that as an exercise and get some answers for this. And it is this helicity flux actually which carries the energy spectrum associated with the corresponding two-dimensionalization of this rapidly rotating flow is determined largely by the helicity flux, which was the first thing that Sagar Chakraborty did for starting out his career. So this was a pretty nice result, Europhysics Letters 2007, of how the flux, how the spectrum changes. But what was obtained over here was a range on exponent over here. So what exactly the exponent should be requires a far more intensive calculation, and that remains, as far as I know, a somewhat open issue. So there is this helicity which comes in. So between energy, entropy, and helicity, we have all the primary players in this game taken care of. And there is 3D, 2D, and rotation, which makes 3D to a 2D. So you have your hands full. Do get your hands dirty also by doing some of these calculations. And tomorrow morning, I'll actually ask you what you got out of it. So beware of that. Try and get something done. And any questions that you may have, I'm here all day, so I mean, you can come and, yeah. Huh.
So in recent years, people have checked numerically and the count seems to be the best.
I see. Oh, very. Yeah, I see. So that bound, I mean, there is a. I see. 7 by 3 as the upper bound. Nobody talks about data anymore, I'm afraid. Yeah, there's an interesting two-dimensionalization, and the fact that it is entropy-driven, and yeah. So, yeah. All right, so